Thanks for the introduction. So this is a problem we started to work on, I think, like a year ago or something. And first we thought I thought I had an optimal result, and then discussed with Eric and John, and then it came out that what I was doing actually could be done much better. And then this is the result that we were talking about. So the question was whether P is important in the P obstacle problem, and you will see soon whether it is or not. And the talk is split into two parts. The first part is the elliptic one, and then the second one is the parabolic one. And you will see a little bit diversities in the cases. So we'll give you good answers in the elliptic case, and we will just leave you there, leave questions for the p-parabolic case, because it seems to be much harder to study. So the talk will be actually at a very simple level. So just skip it. I mean, there is no difficulty anyway, so to skip it. But in the parabolic setting, the p-parabolic setting, the difficulties are much more than we could handle. So it's going to be very just elementary view into that. So you can just relax. It's not going to be anything functional here. Let me see if I get this. Okay. So let me start with the elliptic case, and you all know it most probably. Everybody here knows what the obstacle problem is, and when I'm saying P, so I'm referring to the P Laplacian operator here. I stick to the one and infinity in between them. The boundary data will not be important for the moment, and I guess it will not be important throughout the talk, but I just give it in order to not have questions of that. And then U will always be about an obstacle. So phi is an obstacle here. And then you're looking for a P superharmonic function. But of course, you're looking for the smallest one. Okay. So take all your figures. You have something fixed. You have a picture here coming up. So you have things like this, and you take all the super solutions. Then take the smallest. And this is what we are interested in. Okay, so you have the minimizer. You minimize the functional. You can always have a little bit more. The equation can be changed slightly, then you have to change this, of course, but we'll stick to this case. And this is the admissible case. Well, classically, most people work with this problem by reformulating it. So generally, you look at the difference between U and the obstacle. And if you take the difference, then it's just a simple drill to show that Laplacian of V is going to be F, which is exactly minus Laplacian of phi, times characteristic function. So this holds only on the set when V is positive. So someone, it tells you that if you don't touch the obstacle, then your U will be a solution. If you touch it, it will be that function, of course. If you take the difference, so the difference will be the Laplacian of this minus Laplacian of this. And that's exactly what it is. So you see, everything here is written like a package in one equation. And it's much easier to work with it. And from here, you can actually prove regularity C11 for the solutions in the classical setting, for the Laplacian, I mean. We can prove regularity of the trigonometries. But generally, you cannot do this for nonlinear problems. So you cannot do that. It means that the techniques that you have been using are, well, sort of not worthless, but doesn't work directly. You have to work them up a little bit, shape them up in order to get it to work. So the question I'm asking here is, if I take the function u, solution, and take the obstacle phi, take the difference, so what is the growth rate when they go away? So you do the obstacle, something like this. And if you go away from this touching point here, so the question is, how does it go up? So the rate of detaching. Of course, there are two rates. One is from below, one is from above. And I would be interested in from above. I guess from below is a little bit more technical. Well, in this case, it works.
Well, you have to assume more.
Yeah, you have to say more, yeah, of course. Yeah. You have to assume a little bit more about this guy here. So I will do only from the above. And I will try to tell you what is. Okay. So the first thing one wants to do is see, can we get rid of this P somehow? And if you rewrite the operator like this, right now you just expand it. So this is what we have. And the operator L, let's call this the operator L, and then you see that in the operator L, you don't really have any P. The P value is like a constant. It's not it shouldn't affect the problem in a very bad way or in any. So you see here, if I just go back again, let's see. This is the operator. In front of that, I have the gradient to power p minus 2. So I can just divide it. Well, formally.
You don't have anything in the right hand side.
Yes, if you don't have anything, exactly. So let's, of course I don't have it, so, so in this case it's good. So what you get is basically problem, not P obstacle problem anymore, but the obstacle problem, but without this effect of P. So somehow it means that you're in uniform elliptic case. So P shouldn't really matter here. So, well, bounded coefficients, these are bounded, you know that, and then they're uniform elliptic. So somehow it suggests that P really doesn't matter. Okay. So let me do this a little bit more formally, and we will see that it really doesn't matter. And the proof is very, very simple. Of course, if you put the right hand side, then things different.
But you lost the variational structure.
Sorry?
You lost the variational structure.
I lost, did I? No.
Well, I mean,
Oh, of course,
now
yeah.
your operator
Yeah.
is in non-divergence form.
Question is whether that's important or not. Maybe it's not. I mean, in terms of viscosity, nothing happens here. If you just think of viscosity sense, you touch it by a parabola from the below, and the operator still tells you that it's going the way you want it. So from viscosity sense, it really doesn't matter.
You take the normalized Laplacian in the previous slide when you divide by the
I divide by
yeah, the L is the so-called normalized Laplacian, right?
this
Which is the
is-
interpolation
yeah,
between
yeah.
the Laplacian and the infinity Laplacian, right?
Yes, exactly.
Yeah.
There's the infinity, this is the Laplace. Okay. So a heads up here. So when you have an F, this method wouldn't work. And for the parabolic case, you have a kind of F. So this method wouldn't work with the P parabolic case. One has to find a different way. Okay, let's see what we can expect. And a few things that we, well, one important thing is that P harmonic function are general sigma alpha, but we don't know what alpha is. It's going to be played, this will play a little bit of a role for us, but it's not that important. we don't really care about what this alpha is. A little bit of alpha will be enough for us, then we sort of bootstrap. Okay, so let me just repeat again. Here I'm looking for taking the function u of x and taking the linear part off. So that's basically the function phi at that point. And then I want to see how this goes. Where does it go? We always look at the free boundary point, because if we stay away from the free boundary, we already know that it is C1 alpha, we don't know what alpha is. I'm saying if you go away from the free boundary, I can tell you what alpha is. Not from other points. So this is the effect of that you really have a super solution at that point, and then from below you're touching with a very smooth surface. That's the effect of it. Okay. So classically we know that if phi is C1 alpha, then U is going to be C1 alpha star. Alpha star is just the minimum of alpha and alpha p, and that alpha p comes from the regularity of the p Laplacian. And we don't know what it is. And this is less than 1. This alpha star, whatever it is, that's enough for us to sort of use the regularity and then bootstrap it. So the regularity of the elliptic case tells us that, and this is the result, theorem 1, is that if you take any p in between 1 and infinity, you put alpha between 0 and 1. It can be equal to 1 even. Phi is C1 alpha. Then this is what you're going to get. But the solution is going to be C1 alpha smooth at exactly free boundary points. So if alpha is 1, it means your obstacle is C1, 1. You're actually going to get C1, 1, which is the standard obstacle problem in the standard regularity for the p equals to 2 obstacle problem, which is a little bit of surprise somehow. But of course, once you see the drill at the beginning that you can get rid of this gradient to power p minus 2, then this comes very natural. That is what to expect. What I'm going to do is I'm going to go through proof of this. The proof is very simple. It's just a couple of slides. And then I'm going to talk about the p-parabolic case, which is a bit more involved. Okay. So we want to prove that.
So this alpha only depends on the obstacle, it does not depend on p. That's what you're saying.
Yes,
Whatever
exactly.
is the obstacle,
Exactly,
you get.
exactly.
So you say that if the phi is C11, then your solution near to the free boundary is C1, near to the free boundary.
At free boundary, but not
At the
really
free
at.
boundary point.
It means it decays like r squared.
But that's weird. So off
That's
the
very
free,
weird.
that's weird. Off the free boundary is less.
Yes. Free boundary, yes, free boundary gives you better regularity, which is actually the reverse in the classical sense.
That's what I'm saying. That the free boundary.
Well, it is not so surprising because in there are results that tells you that actually boundary, if you look for instance, elliptic equations which give you, let's say, C1 alpha regularity inside on the boundary, fixed boundary even, if you put good data, they will be forced to behave better, much better. But this is kind of like that.
So if constancy depend P can go infinity.
Yes, but I don't think that doesn't matter.
Doesn't matter, you can take a limit.
It's not a big deal.
So infinite Laplacian automatic
We didn't try if this goes for infinite Laplace.
No, well,
She
it
depends.
wouldn't go through because somehow we
C
use
depend
that.
P.
So this.
Yeah, you cannot put it to one.
So now you guys are going to use a non-divergent structure of the equation.
No.
So then I'm asking you something. So suppose now you have a divergence form equation, a linear equation. Divergence divergence from equation with Helder continuous coefficients, do you still get C11 If the-
I guess one gets C11.
if the obstacle is,
Yes. Yeah, we get C1.
because again.
We didn't
of-
do that, but we got it.
Because again, if you have Helder continuous coefficient of the obstacle, you can't get any better than C1
Yeah.
alpha.
I'm not sure if that is done. I think this might be even known. We have a lot of new references. We digged out a lot of references. Might be even known, I think.
It is known or not known?
It might be known, I don't know. We did out the articles and papers, but we didn't read it. It's too messy. So I'm going through it. But I guess we have a few articles telling us.
But it would be in the same spirit of what you're proving here.
Not really, no. Proof
Yeah.
are-
I mean, you have a divergence from equation with Helder continuous coefficient.
We have a divergence for.
Yeah, of the obstacle, your solution is gonna be C1 alpha at best. You can get
Yes.
C11, you don't get to C11. But then you're saying that at the three boundary points, you actually get better if the obstacle is better.
Yes.
Mhm.
Well, we have to probably look at the articles. Nobody wants to read. But there might be something there that is still in this kind of.
Mm.
Yes. Okay. So let's see how we do. So the idea is very simple. So the idea is that has to do with if you look at the scaling. So the problem is when you want to scale the P Laplacian at the point when the gradient is not zero, then you're in a little bit of trouble because you have to subtract the linear function. And when you subtract the linear function, the gradient of that is not the gradient of the original one. There's some constant coming with it. But if you split it, if the gradient is zero, then you see that really is like scaling linearly is like scaling the function. The gradient of the scaled one is like the gradient of the old one, and it still satisfies the P Laplacian. So the problem is.
And that's what works in your figure, three boundary points, in a way. I mean, as a
Yeah,
fact
if the
that-
gradient is zero.
Yeah. the
But if
fact
it's
that
not
you-
zero, then it's a problem.
Yeah.
Then you have, of course, classical result.
Mhm.
But the problem is how to link them. So this is basically that simple idea. So you start with these things that you already have. U is equals to phi, exactly at the free boundary point. The gradient is gradient of phi, exactly at that point. And now we are assuming that the solutions are C1 alpha or some or C1 alpha star or something, that we don't know what this alpha star is. Okay? This is what I just gave you a few slides before. Also, if you just put the equation like this, not the equation, but the function, ux minus uy, and use the obstacle, then you see that this is going to be larger than minus c r to the power 1 plus alpha. Okay, so this is given to you through the obstacle. So what you need is actually things from above. This is what you need to prove. Okay, so we split it into two parts, small and large gradient, and here it is. So choose R, that's small enough, choose your 300 point, and look at the points when the gradient are small, in this sense, and then the gradients are large in this sense. Two sets. Well, this would be enough for you, basically, or 2R if you want, or R. Well, I guess 2R here. So if the gradient of U is 0, then you're covered by case 1. Which is actually the straightforward. So for the second one, you have to use the first one, scale it, and then use a slight elliptic theory. Okay, let's do the case 1. Gradient is less than r to the power alpha. It means that that this function is less than. If you prove this, then you see that this is what you get. Just because this gradient is less than r alpha, and then this is less than r, so the whole thing is r to power 1 plus alpha. You can just put it on this side. So it means that this is enough in order to get what you want. So we prove this. And you see already that you're getting rid of this linear part. This is the trick here. That's the only trick, basically. That if you just notice this, that this is true, it means that you don't need to work with this function. You need to work with this function. And the gradient of this function is exactly the gradient of u, because this is a constant. And the operator is not changing. Okay, so I would say the whole thing in the first part is to notify that you get this. So enough for us to prove this. And well, what you do, you scale it. So you take a scaling with this R, and this is the scaling. If you would have, again, I'm repeating, if you would have scaled with the linear term, so it would be the gradient of u, then the operator is going to change. I don't want to change the operator because I cannot handle it. Maybe somebody can, but I cannot. So in this way, I don't need to change the operator. Okay, what happens is basically that you have a new problem here. You have a new obstacle problem. Phi tilde is the new obstacle. You have a good control of that. L infinity is bounded by this. And I'm here using that gradient of phi and gradient of u are equal at the point y. And this is less than r to power alpha. This is the case. So this is going to be less than, and I'm going to get exactly this estimate. Okay. So once you have this, you notice that you have invariance under scaling, and it means that u tilde is defined, we solve the p obstacle problem again with this obstacle now. Okay, so now we can use the weak-Harnack inequality. So I'm going to use weak-Harnack inequality. Weak-Harnack inequality is applied to non-negative supersolutions. So it says that if you have a non-negative supersolution, the L, some norm Ls, I'm calling it here, is going to be controlled by, let me see, am I right? L is going to be controlled by the infimum. And then I need the subs to make a sub-solution and get the sup is controlled. So I want to have LS controlled first and then pointwise control. So I have to first make super solution to be positive, then I have to make a whole change of my function to make it sub-solution in order to get the other one. The proof is a little bit different, but I think Eric found this way of going around easier. Okay. So if you do, okay, this is what you want to use. So LS norm in a ball of radius R is less than infimum in half that ball. But of course you need non-negativity. Okay? But we had control already from the below, and that's enough for us. We already had control, so u tilde plus c is larger than minus u
When
tilde.
you say now you have a negative super solution, so which equation now? It's your normalized.
Just to be Laplacian. Because
The normalized version.
oh yes, no.
Everything is for normalized version.
That's still P Laplacian.
Oh, still Philip.
Yeah, P Laplacian is not changing. I don't want to change that.
Okay.
Equations and functions is changing, not the operator. So I'm just adding a constant, still a solution to the P obstacle problem. The obstacle is 0 now. Yes, larger than or equal to 0. The obstacle is changing now, but we're not going to get larger than or equal to 0. And this implies that I'm going to get with R in 3/4, and this is exactly less than the infimum. And this infimum is of course less than W at 0, let's say, at that particular point I'm choosing, and that's exactly equal to the obstacle, and this is less than some C1. So I'm going to get control of LS with some constant. So next So next would be to take something similar, but for the making a sub-solution and take the supremum is bounded. Okay, so let's remember this. I will be back to this again. So in terms of U, so this is W. In terms of U is just U tilde plus U0 is exactly again the same thing with a different constant. Because W was just U plus a constant, so this is going to be the same thing. Okay? So let's go to the supremum norm of U and try to estimate that. But we need a Harnack inequality for the subsolutions. So how do we reform the tilde U to make it a subsolution? It's not so obvious. You have a super solution, you want to make it a subsolution. But what you do, you basically cut it at the free boundary. Lift it and cut it. So here is what we do. We take the maximum of the function W, okay, and then of this value. So whether it is below that, you cut it. And you know that this function W is actually, this was the U tilde plus constant. So the constant is nothing important. U tilde is a solution when it is not touching the obstacle. And this is exactly when it doesn't touch the obstacle. This is exactly what happens. So it tells you that once you are trying to touch the obstacle, you cut it. And you have a solution, and you cut it. And the picture for going from the solution to the minimum value of that is this. So if you have something which is a solution here, and you cut it, then it's always a sub-solution. So together, it will be a sub-solution. Okay, so you have a sub-solution, and that's basically enough for you. Well, I'm just doing the drill here. What I told you is W is this one. So V is going to be exactly rewriting the whole V like this. And then U tilde minus sub phi is of course 0 in this set. This is the set. Okay? So you cut it. That is going to be a subsolution. Okay? Once you have that, then you have the supremum of V is going to be less than the LS norm of that in a larger ball. And this was already controlled by a constant, and then you have basically that V is bounded. But V is the scale function. You have scaled it. So you have this R with you. So supremum of U tilde is less than this, and this is less than a constant, and that's all you needed to do. You already have this at the beginning, so it means that you have basically a good control both from below and from above for U tilde. And that tells you that at that scale, the function grows exactly like R to power 1 plus alpha. Okay. So that was case 1. It came with 2 inequalities. So it was just 1 scaling and 2 inequalities that helped you, and 2 Harnacks. So for the case 2 is when this is much larger than R alpha. And so it means, well, you have to think differently. You have to think when R, you take a point Y and the gradient is a value. You take R's that are small compared to this value, then that's the first case, we did it. Now R's are much larger. So what happens if R's are much larger? So what you do again, you do this scaling. And this again is bounded because of the regularity of phi and phi tilde. So classical results tell you that U tilde is actually C1 alpha star. Here is where you use it. Alpha stars comes in, which is regularity of the P Laplacian. But then, now, gradient of U tilde 0, gradient of phi 0 are the same, and they're equal to 1. So what does it say? It says that you have actually a kind of elliptic problem now to work with. Because gradient of u0 is 1 here, so the whole P Laplacian at that particular point is uniformly elliptic operator. Okay, smooth coefficients. The question is to get the uniform neighborhood of that. For that uniform neighborhood, you actually get
C1
exactly, you get from this, that you have a uniform neighborhood. So the gradient of u is going to stay larger than 1/4 or 1/2 or whatever in a uniform neighborhood. Then you just run again for the classical, with the classical theory. Okay, so I'm going to go a little bit faster here. So once you do that, once you have the first one using these Harnack things, then the second one is just the scaling and using classical results that locally at that point you have uniform elliptic operator. You don't need to worry about anything. And things are smooth also.
Yeah,
On top
the
of that.
gradient, so you are using the gradient is C alpha,
Yes, that,
But
that,
this-
that is given to me classically.
but this will depend on P.
Yeah.
Yeah, you just use it qualitatively.
It's a little bit of
And you
neighborhood.
just to use it qualitatively,
A little bit of neighborhood.
Yeah, okay. and then you don't use the quantity.
No.
Okay.
Well, I mean, the constant in the end is depending on P.
Yeah, the constants will depend on. But
It
the raw
only,
you
in
cannot
the
get
end,
rid
it
of.
will only enter the constant.
Yeah, the constants depend on P, but not the power of the decay. The power of decay is important in regularity theory, not the constants. Constants depend always on dimension and everything else. Okay, so this finishes the proof. Well, you get let me not discuss this. You get non-degeneracy directly for C11 case, but we could go below that. I don't need anything else. We'll go below C11. And then you get porosity of the free boundary.
Yeah, that's what I was to ask you. So you do get,
Yeah, you get this, yeah. But we can, I still think we can get below C1 alpha, but we didn't like that. But okay, we didn't write it, but I believe it's okay. So let me go to the P parabolic case, which is actually more interesting and much harder. And
Let me ask you this question now before you change. So this is true from P equals 2 to P equals infinity.
no,
P is
from
1 to
P-
infinity.
From P1 to
From
infinity.
P1.
for this one is now I'm gonna go stick to P larger than 2. P parabolic, I'm sticking to P larger than
In the previous case, P not equal to 1.
larger than 1, less than infinity.
Yeah, you need.
But then it is not an interpolation. I mean, between 1 and 2, it is not an interpolation. So it's very interesting that it works for
It
P between 1 and 2.
doesn't care about the p-value, as long as you have those Harnack inequalities.
So that's what I'm about to say, isn't it enough to have P bigger than 2n over n plus 2 here? You only need the weak Harnack inequality.
Here, no, here we do it a little differently. Scaling comes in, so the Harnack inequality didn't help us that much
Hmm.
here, but yeah, it would be a completely different proof here. So we are looking now to this into this operator. It's called the P parabolic one, and you see already that I'm going to go a few slides with simple scaling things, and you will really see the diversity of the things that can happen. Okay, and remember the strong maximum principle phase for this, and that is already very bad news. Somewhat good news because you can do other things also. And the Barenblatt solution is one of those. So here's the Barenblatt solution. The picture is like this. You start with your hydrogen bomb or whatever it is, and then you just let it go, and then you get something like this. Here is plus, solution is positive, here the solution is 0. And this actually solves the equation itself, so it will be at every point.
So if we are on the Earth, it will not affect us?
No, you have to stay in the right place. This is high. And this is low. So you have to go, you can go up a little bit. So, okay, observe that the equation actually is passes here and doesn't produce any measure. And if you see that it has a very interesting feature, it's very complicated writing, but don't be bothered with all this constant. So these are a lot of constant, don't be bothered with that. It's really not so important. So I'm going to give a little bit more examples. So what is this? This is actually, it behaves in two different ways, and the question is whether we can see that. So one is that the obstacle is 0. Okay, so the function can be seen as a solution, as a solution is a super solution, and it is larger than 0. So this really solves the obstacle problem with 0 data. And can you see the behavior across the 0 here? There's a picture here. Look in the x direction. What is important here is, in the x direction, let's say t is positive. This is just a constant for you. And x to power something minus this, well, this power is not important, strangely, because you're cutting at here with this power. So the power is actually p minus 1, p minus 2 over p minus. So it goes quite fast. It goes with 1 plus 1 over p minus 2, very fast. So the derivative exists for x direction, and it goes to 0 quite fast. Also, the time derivative is actually 0. You can see that. And let's not drill that. Yes, if you look at, okay, my question here is, there are two different behaviors. The next one, if you look at the function minus bp, so sort of do it like this, and then, so the picture is something like this. It goes infinity here, it goes like this, okay, it goes infinity like this, and then it goes to 0, flats out. And here, you have another behavior, exactly on the, when x is 0, you have another behavior, because at x is 0, then this power plays role. So it means it has a regularity which is of power p over p minus 1. So there are two powers here, actually, already in the variable solution. And you can see this as an obstacle. You hear of the obstacle problem. One behavior is this, the second behavior is this. And this is the obstacle for the second one. If you put x to it, 0, and this is what you get. Okay, so here's a lot of examples. The one that John found is this one. Very
So
simple.
is this the reason for which you need p strictly bigger than, or well, bigger than?
No, I mean for Barnblatt, yes, but otherwise, this one, any p, is between 1 and infinity. This is a solution. The obstacle is t, and this is the solution.
Well, that's actually, for p between 1 and 2 is even better than C11, right?
Yes, p, when you go below 2,
That's-
then things are going to become
that's-
better.
yeah.
But this, when you're above 2, things are a little nasty.
But for p less than 2, you don't get the other free boundary.
Which one?
The Barenblatt solution is different.
Yeah, it's different.
P is
Yeah.
less than 2. You get only one free boundary.
I haven't even seen that. Maybe I should check.
Written around.
Okay.
Look at my book.
It's written around, look at my book.
Okay. The
That
next
free
one
boundary is only for p larger than 2.
So the next one is this, and here phi is 0, the phi is 0,
Yeah.
and you just cut it. So the solution are sort of traveling wave solutions. It goes like this, and then the power is p minus 1, p minus 2, so it goes in the x direction. Sorry, in the x direction it goes like this, fast enough to 0, and then it travels. Okay. And then t also has the same behavior. It has both x and t, same behavior. So regularity in time is very good as well. So it means that the time derivative of this is 0 at the free boundary. The time derivative of this is constant. The time derivative of Barenblatt is also 0. I found another one, actually, a few weeks ago. Thought to take it up here. If you let t be negative, so this value is positive now. And you look at this, you're going to get a different behavior. And the power here is p over p minus 2. This is the largest power we found. Question is whether there are other powers. Okay. So how many different rates in the x direction do we get in these examples? There are 3 rates. This rate, this one, and this one. And this one is the fastest, of course. And the question is whether we have others. Okay, so let me do a little bit of exercise before I go through the statement of what I want to prove and then give you a sketch of the proof. So if you just play with this, so what you think, suppose you have a solution which is kind of homogeneous, so you want to see the scaling around these free boundary points. This gives you good information of how the behavior should be. And what, well, not should be, the possibility of the behaviors. And then you have to go and prove it, of course. So I'm assuming that function is 0, these are positive constants, and you think that, so what kind of information do you extract from here? Let's say if A is 1, and this stays bounded, so you have to have UR bounded. Suppose UR is bounded, you don't know that. But if UR is bounded, and A is 1, it tells you that U is Lipschitz in the x direction. That's what it tells you. For the heat equation, usually A is 1 and B is 2. The heat equation tells you Lipschitz in this direction, half Lipschitz in space. Of course, you can go up and down depending on what you want to do or what you have. If A goes up, larger values for A, it means that you have less regularity. So just remember that. Larger values for A, less regularity. If you want to do the drill with the line and the x-axis, think like this. If this is x, how far do I go away? And then what is this length? And this is, I keep r. Okay? So well, this is r, so this is rx. And then the question is, what is this value? Okay. So that's exactly the regularity. Okay, simple computations. If you let the heat, P Laplacian heat operates on the UR, then this A and B comes out. And the condition for U, in order to keep the equation, invariance, you will have to impose B equals AP plus 2 minus P, or A equals this. This is, you cannot compromise on this. These are given to you from that you have the equation, the operator intact. So what are the plausible or possible rates? And so you see that each time, well, you don't need to read this, but each time A and B passes a certain value of 1 over k, you have to subtract something, but let's not stick into that. So if A goes up to k, then B goes up to this value. And it tells you that if k is, for instance, 1, then use Lipschitz and in x and half Lipschitz in t, regardless of p. Doesn't care about p. Which is, I don't know, strange, maybe. Okay, what happens if we let A be larger than 1 minus 2p? Okay, and it goes down to that value. Then it tells you that B is going down to 0. And this is actually a strange behavior. What does it say? It says when A goes to 1 minus 2p, that gives you an exact regularity in the x direction. And the exact regularity is this. You always have to reverse this. So the regularity is reversed. So this is p minus 2 over p. It means that p over p minus 2 is the regularity. Okay, this is the regularity in x, but b is 0. It means infinite regularity in time. I don't know, have you seen that coming? Or? So you get infinite regularity in time, which is very strange to me. Which is very, I mean, you can really, this is not a statement, not a proof of anything. It tells you what can happen if you could work it out in this scheme.
Yeah, but this is like
Yes, it is like time in time, okay, that could be, but if you.
Because the scale is
Yeah, but if it's not,
intact. You
yeah,
don't
but
move
if it's
it.
not time independent, if you don't go into that limit, then, okay, more here. Let me see, I'm losing too much time here. So other interesting values are when they're both equal, and this is exactly the one with the barn plot across this, the real free boundary. This is exactly this. So you get this regularity. And then another one is when b is 1 and you get this one, and then you get Lipschitz in time and this regularity. And the Lipschitz in time is probably what, I don't know, I mean, this is maybe the worst one, I don't know, for the obstacle problems at least. The other ones, the time derivatives are better. Of course, if you want to look at the singularities, then you look at the function which looks like this. Not divided by r, but multiplied by r. That gives you the rate for singularities, and you can now, it was 2 minus p, now it becomes p minus 2. And you can start playing with that, what kind of singularities you get. Of course, this is just a simple exercise, but this gives you an idea of what things to expect, if there are any things. So any serious analysis probably should look at this, say, okay, this is a possibility. Let me skip these things here. Okay, so this is the theorem. So let me state it and just give you a short proof of this. The proof is different. So the assumption is that to an infinity, okay, I'm working in a half cylinder. So I take a free boundary, whatever it is, and I'm looking at this. Okay. This is my center now. So I'm looking for the cylinder below, and the cube below. This is the assumption I'm doing. In the paper, the assumption is the time derivative is bounded from below, but I'm going to assume it like this. We have some Holder inequality that we start to become a little bit, we have to redo that maybe, but I believe it's okay. I'm going to stick to this case. Here, it was very fast. Otherwise you have to do with a lot of Holder regularity and a lot of constants. I mean, you don't want to see that. Okay, so here now is, this is what I'm stating, this is the result. That if you take the power, this is the worst power, it's p over p minus 1. Because we had other powers which were p over p minus 2, for instance. You don't get those. And of course, it seems possible to get those if you assume something about the time derivative. So we're assuming that time derivative is bounded, but if we assume that it's, let's say the free boundary goes to 0, maybe we can bootstrap this a little better. Okay, so I'll forget about these things. So what you want to prove is that in the space, you get this power rate. So ideas in the proof is simple. Let me see. Yes. So we do this first, and then the other one is again by scaling. So we assume that this is small enough. We're just looking at R, which are much larger than the gradient at that point. And I'm looking again at the difference of this, not the linear one. So I want to skip that changing operator. And this is the reason I'm assuming this at the first stage. Okay, I want to prove that this grows like this. And the idea would be, if it does not, then you just take the largest constant j each time that appears. So you take 1, 2, 3, etc. And each time you will have a sequence of rj's that will agree with this inequalities, and then it will be exactly equal for that particular rj. So r is larger, then you get that this is controlled, but if r goes, you see, when r goes towards 0, then s of r might become much worse than r cubed. So it's like, okay, here we stop, we call it rj. and then I do the next j. I go for a number, let's say j plus 1. And then I go, and then I stop. I go, and I stop. And everything above that is controlled. And exactly this one is equality. So here comes the scaling. And if you're familiar with the P parabolic problems, then the scaling is actually, you have a diversity of scalings, as you saw already with A and B. But here, since I'm having not, I have to divide by this in order to control the whole thing. I want to say that this is bounded. In order for this to be bounded, I have to divide by the sup value. And this is exactly the sup value. This is the sup value, then I have to scale it like this. Now the equation is intact. I still keep the equation. Okay? This is bounded, and Vj still satisfies my equation, and I have a bunch of information that I can extract. And super solution to the scale problem is uniform, continuous, and compact sets. Scaled obstacle will tend to 0, and that is very important fact actually, because my obstacle is smooth, but now I'm dividing with something very large with respect to that smoothness. And that large in below will of course kill the whole thing. Vj at 0 will go to 0, because again the obstacle is bounded, but you're dividing by something much larger, so it brings down, and the function goes down with it. And V0 in the limit will be larger than or equal to the obstacle. This is the limiting obstacle. So what you have is a parabolic super solution at the end, which touches the 0 point. Now take a super solution which is non-negative and has an infimum. That doesn't sound so good. Super solutions don't have infimum inside. I mean, sub-solutions take maximum on the boundary, super solutions take infimum on the boundary. So my super solution here is non-negative, and it's 0 at 0. So that sounds like a trouble. At the same time, my function has a supremum norm which is 1, so it's not identically 0. So the minimum principle should be violated, or say that this is a contradiction. Well, the bad news is that there is no minimum principle. So this means that it can happen actually. Okay, and you have to show that this doesn't happen. Now let's not forget about this assumption we had. So that assumption tells us that things are maybe not time dependent. Because for the P Laplacian case, we have a strong minimum principle. If things are not time dependent, then I could say, okay, I have a solution which is time independent and has a 0 inside, super solution, and its maximum is 1, so something is violated here. Okay, so here is just a simple drill here. You take the difference between the value 0, time, and another time, whatever you want, and then you see that this is going to be bounded by the time derivative with something here, which I take 1. And if you take the derivative of the function Vj, then these guys come out here. It kills Rj, which is below this Uj, it kills it. And what is left is this guy here. And you remember it was power 2 minus p. We had the power of j power 1 and Rj to power q. Rj power q, Rj power q goes. 2 minus p is 1 is killed and 1 survives, 1 minus p. As j goes to infinity, and because the derivative is bounded, this guy is bounded, and the whole thing is bounded by j to power 1 minus p. If p is larger than 1, or for in our case larger than 2, then this goes to 0. And the question here would be, where did I use p is larger than 2? Because here I really need only 1. You know, p is larger than 1. But it's actually comes in at the point. You know. Okay. So the minimum principle so it's time independent, so you have an elliptic problem and things are, I'm sorry, I have still a few minutes. But but I think I'm done. Okay, thank you.
Questions or comments?
I guess you, I mean, you mentioned that you haven't seen any other dependence in the x direction, but I guess you can produce, if you have a p-harmonic function, you can produce solutions to the p-parallel equation. And in 2D at least, you have more or less a representation formula for all kinds of power behavior.
What do we have? I didn't get the
You
first
can
part.
produce p-harmonic functions more or
Okay.
less with the behavior you want in 2D by in the formula by Manfredi and Ivanyi, for instance. And then you can combine that to get a solution to the p
I see,
parabolic equation. I think you
okay.
can actually produce quite a
Okay.
few different.
But that's two-dimensional, but that doesn't really.
Yeah.
Yes.
Anything else?
I guess it's pizza or?
In 15 minutes, yes. But let's thank Eric again.